So I've acquired some titanium, and having never worked with it, I thought it'd be interesting to play with it, just see how it cuts. I've heard stories of the fact that one of the big difficulties with it is that supposedly, what I've heard anyways, is that unlike steel where the chips tend to take a lot of heat away from the item being cut, that in titanium the heat stays in the part and you have to use a lot of coolant. So maybe we'll look into a couple of these things, see how it works out. Let's just do a facing cut here at 440 RPM, see how that works. Notice quite the interrupted cut. The end is definitely not flat saw cut. So let's give that a try again.
So a little bit of extra information here. The piece of titanium I'm using is about 4 inches long. I bought some cut-off ends on eBay. The reason why you don't see it used a lot, for one thing, is because it's incredibly expensive. This little 4-inch piece, if I went to buy it, it's 4-inch long by 1-inch diameter. It'd be about $40. So just to give you an idea.
Still not a big enough bite. It looks like we're still getting a bit of interrupted cut there. So I'm going to work my way back out and do 25 thousandths. So you'll notice it's a bit plastic. It's kind of pushing some of the material ahead of it and folding it over, which is kind of interesting. So let's see if there's any evidence to the heat thing. Oh yeah, boy, that's that is seriously hot. Wow, and still not flat. That's very interesting. Let's try a bigger cut, see how that works out. Let's try 50 thousandths. So the chip breaker's not working, but I guess I sort of would expect that. This is for steel, not exotic metals. Boy, I can smell how hot it's getting. So the finish is not particularly great. Well, it's smooth. Woo! Too hot to touch. That's interesting. Let's see if I can check it out with a thermal camera.
So as we can see from the thermal camera, the temperature of the part's 390 Fahrenheit, which is about 199 Celsius. The part seems to be taking most of the heat, and the chips were all cool to the touch.
So for comparison, here's a piece of cold roll. I'm sorry, this is the 4140 chromoly, so reasonably hard stuff. It's in its annealed softest state. Let's see what kind of temperature changes we get here. Cool to the touch. Very different.
So as you can see here in the thermal view, the workpiece is only 91 Fahrenheit right at the point of cutting. The 4140 definitely cuts a lot cooler.
So next, let's just take a look at how a longitudinal cut looks. I gotta say the finish is rough. It's shiny, but it's not exactly even. Like the material's hard enough to deflect the cutter. Let's just see how it does with longitudinal. So this is a 25,000th depth of cut at a very slow feed rate, incidentally. Oh, that's a very pretty finish. All right. Yeah, that finishes really nicely, actually. But the way it cuts, look at that. Sort of smears. It's very unusual cutting stuff, but that's a really pretty finish. And it is hot. It is really hot. Much hotter than the 4140. That's kind of interesting. So, that's just a little something. I thought I'd show you some titanium. I was always curious of how it worked. It looks like it'll finish just beautifully. It's probably why they make men's wedding rings out of it. But other than that, my cutting tools seem to deal with it all right. The chip breaker is not quite right for the cutting rate that I'm choosing. I could choose a much faster cutting rate and see what happens. Let's try that. Okay, so we're going to go from what was 2 thousandths revolution to 10 thousandths of revolution. We'll do the same 25 thousandths depth of cut. Let's see. So set it at about 25. Let's see what happens here. Wow, still an excellent finish. All right. If we go back in, and now we keep going, that'd be 50 thousandths depth of cut. Finish is great. Boy, I can smell that. You can smell how hot it gets. Yeah, it gets really hot. Now I see why they say use lubricant and constant flow, because this stuff really cooks. But the finish is wonderful. I could get spoiled by that.
So here's some titanium being bored. I had taken some shots of it being drilled, but the camera decided the swarf was a lot more contrasty and focused on that, so the shots weren't any good. It was extremely hard to drill. By the time I got up to ½ inch, it really took a lot of force, and it was getting really hot, so it was burning the lubricant I was using. Hence, again, the need for significant amounts of coolant when you're machining titanium. This is a really small diameter boring bar, so that's why it's squealing, even though there's not a lot of stick out, but the material's pretty hard. So I'll save you the trouble of listening to it squeal.
All right, so my previous footage ended up focusing way down here because the chips were higher contrast than the titanium part I was cutting. So I'm going to supplement. Also, I'm going to cut off some pieces so that we can take them over and watch them change, watch the oxide layer build with heat, and watch the colored interference patterns grow, so you can see how you can color parts. Also, at some point in the future, I'll try and demonstrate how you can do that electronically as well, using DC current to build an oxide layer to create color on titanium parts. So I'm just going to part off a couple pieces here so that we can show it, and you can again see how titanium cuts.
You might be wondering why during a parting operation I'm not using lubricant, and it's because the titanium gets so hot that it starts to burn the lubricant. So what I really need is coolant, and I really haven't gotten up the guts to use flood coolant in my lathe yet because I'm worried about rust. So I do it dry, and it works out okay. But I got to be careful because I did see a couple sparks a couple times, and I think it'd be possible to light the ignite the swarf if you're not careful.
Okay, there's one. Let me clear out some of these chips. Gotta tell you, it is hot, hot, hot. And I'm also going to demonstrate how flammable titanium chips are. So titanium is a lot like aluminum, and the reason why it's so relatively impervious to oxidation or rust is because it forms a passivation or an oxide layer over the surface very, very quickly. It has an incredible affinity for oxygen. So as a result, when you make really high surface area titanium turnings, once you heat them up to the point where that oxide layer can get compromised, they combine readily with oxygen, and they burn a lot like magnesium, very, very bright and hot, which is probably explaining why when you're cutting these parts, the chips don't take away as much heat. Well, it seems like the chips don't take away as much heat, because I am guessing that because you're exposing brand new titanium metal, it's oxidizing rapidly, and as it's oxidizing, it's of course being exposed to oxygen, and it's combining with that oxygen, and that's an exothermic process, which means it generates heat, which will heat up the part even more than just the friction of cutting wood. So another interesting bit of history, I have some titanium swarf here, and in the manufacture of titanium, when they're melting the titanium in a crucible, they cool the crucible with a water jacket, and on several famous occasions, the water jacket ruptured, and you end up with a dual explosion. First, the water hits the molten titanium and immediately vaporizes, forming steam. And steam, being a much higher volume for the same amount of material than liquid water, creates an overpressure situation and blows up the crucible. Then, because molten titanium wants to combine with oxygen so badly, it strips the oxygen molecules off the water, creating titanium dioxide and H2. H2 would be hydrogen gas. hydrogen gas is incredibly explosive, and there causes your second explosion. So I'm only going to demonstrate the combustion part here. So what I was doing was heating up the titanium to the point where the oxide layer is compromised, and then it readily combines with oxygen, and it burns very, very brightly, and a little bit reminiscent of the way magnesium burns. The byproduct, as I said earlier, is titanium dioxide, which is relatively inert, non-toxic. It's the base for almost every paint you buy and any other white things, also used in a lot of food products to make white colors. So a bit of trivia for you. So another very interesting feature of titanium is that the oxide layer can be manipulated to create colors. So I'm just cleaning the oil off of the part right now. And I'm not going to do a very careful job because this isn't a critical part, but when you're doing this for real, it's very important to have a very clean part if you want even and good results. So, so here I am with the part, and see, I might need to make this a little wider so you can see. Let's see, is that? Pull a little bit wider here. Okay, so we're going to light the torch, and so when you're heating the titanium dioxide, you can make the oxide layer thicker, and once you get to a certain thickness layer, you actually create an interference pattern, which is the thing responsible for making birds' plumage other than brown. So parrots with all those bright colors is actually caused by interference patterns. So the oxide layer, some light will bounce off the surface of the oxide layer, some light will penetrate the oxide layer and bounce off the base metal. And when the thickness is just right so that they cancel out, you will start canceling out colors and be left with, you know, whatever colors were not canceled out, and so you can actually control the color of titanium. This way I'm doing it is with heat. You can also do it electrically, which maybe I'll be able to get the equipment and demonstrate that for you as well. Let's start with this way. So as it heats up, the oxide layer builds, and you go from yellow and amber all the way through blue to purple. So parts of it are already starting to change. This is a very small part. I might be overheating it a little bit. So here is the part with mostly gold, with one spot that I heated a little more that is now turned gold. Hopefully you can see that. One thing to remember when you're doing this is that you need to stop short of where you want to end up, because the part's hot and it will continue. So now it's shifted to blue, and I've heard that you can even get green out of it, but it's a very tight margin to get green out of it. That you have to be able to get just the right temperature to get just the right oxide thickness layer. So there we are with blue. So as I keep building the oxide layer, I start to lose the color that I had before, the blue. You see a little bit of rainbow there. Let's see if I can get this for you. And you start to lose the blue because now the oxide layer is getting so thick it's not interfering anymore. And now the part ends up sort of brownish beige.
Thanks for watching. Hope to see you next time.